Hello and welcome to Lecture 2 of Superposition and Interference of Waves in Phys 1201. And this is the first of two lectures that will be looking at standing waves. At the end of last lecture, we saw that when two sinusoidal waves that are identical except that they're going in opposite directions meet, we get a particular distinctive pattern, and we call that pattern a standing wave. We can understand how it works by looking at a sequence of snapshot graphs. So what I've got here is I've got two waves that I can move around, and they're identical except that I've drawn arrows on them to indicate which way they're going. And they're going in opposite directions. So at the moment, remember that the total displacement of the medium would be the sum of the displacements due to the two waves. So it would look like this. Roughly. So note that we have large peaks and large troughs at the moment, and I'm going to call this moment t equals 0. Now, if we go ahead by a quarter of a period, so I'm going to go to a time that is a quarter of the period later. Now, remember that in a full period, the wave travels a distance equal to the wavelength. So in a quarter period, it has to travel a quarter of the wavelength. And that means that this crest is going to be where this crossing is. So I'm going to move it a quarter of a wavelength this way. And similarly, I have to move the other wave a quarter of a wavelength the other way, like so. And if you now look at what the total displacement would be, well, look here, we've got crest on top of trough, that's 0, 0, and 0 is 0, crest on top of trough, and so on. And in fact, no matter where you look, they're mirror images of each other. They're going to add to 0 everywhere. So at the moment, we've got a flat line. Now, I just want to point out that before, there were places where the displacement was 0, here, and here, and here, and so on. And there were places in between where the displacements were big. Now let's look at a quarter cycle after that. So what we were just looking at looked like this. But now I'm going to go another quarter period. So I move this one a quarter of a wavelength this way, and I move this one a quarter of a wavelength this way. And look at that. We're back to constructive interference where crests are on top of crests and troughs are on top of troughs, and so on. And notice that the places that had 0 displacements, once again, are places that have 0 displacements. So we have some places where no matter what time we look at, the displacement is 0. And halfway in between them, we see crests and troughs. And notice here's a crest. If we look half a cycle earlier, at that time we see a trough. So this place is alternating between crests and troughs. The sequence of snapshot graphs I just showed do demonstrate the idea, but perhaps an animation is better. So I've made this animation, and you see I've got two waves. The red one is going to go to the right, and the green one is going to go to the left. And the blue is the total displacement. So if this was a string and these were the counter-propagating waves, the green and the red, the blue is what you would actually see the string do. And here we go. You see that we have places here, here, and here, and here, where the medium doesn't move at all. And halfway in between, we see places with maximal movement. And this blue wave doesn't seem to be going anywhere. It's just wiggling back and forth. And so this is why we call it a standing wave. And I'll just stop it at a few moments. Here is a moment when crests are right on top of crests and troughs are right on top of troughs, and the medium has large displacement at these places. And if we look a quarter of a cycle later, here, roughly, we see very little displacement. It's useful to be able to draw a representation of a standing wave that gives an impression of all of this. So if you think about what a standing wave looks like, at one time, and let's call it t equals 0, it might look like this. And let's say this is a moment when we have maximum displacement at the places that are moving the most. And half a cycle later, we know that it'll be flipped, that the peaks will now be troughs, the troughs will now be peaks. And so the way we draw it, just to give this impression of a standing wave, and it helps us to talk about them, is that we just superimpose those two like that, and this is how we will typically draw a standing wave. Now we're ready to talk about the anatomy of a standing wave. So we know that when you have two waves, one going right, one going left, they combine to make a standing wave. And we know that there are places like these where you have maximum displacement and that they oscillate back and forth with large displacements, and areas in between where there's no displacement at all. These have names. We call the places where no oscillation occurs at all nodes. And the places where maximum displacement occur are called antinodes. And something to notice about the nodes and antinodes is their spacing. That if you superimpose one of the waves that makes up this standing wave on here and look at its wavelength, you can see that one wavelength carries you the distance between not the next antinode from where you start, but the one after that. And so the distance between antinodes is half of the wavelength, and similarly the distance between adjacent nodes is also half a wavelength. Now we come to an idea which looks sort of trivial, but turns out to be really, really important. Now for some reason I find students have trouble with this idea, but right at its core, if you look at what we're talking about here, this is very simple. So here we go. It's an idea called path length and path length difference. So let's think about a wave that has just been emitted from this source. And we want to look at this wave's arrival at some point A. So let's track the leading edge of this wave. Well, very simply, the wave moves along and eventually it arrives at A. And the distance that it traveled, which is just from the source directly to point A, is called the path length. So I'm going to call this path length R1, and if you notice, it's just 1, 2, 3 meters. Simple. Set that aside and let's look at, from this source, you would have also had a wave go the other way on this medium at the same time. I'm not drawing them both, but both of these waves would have left this source. So that wave will also reach A. Now I've drawn fixed walls, so these are hard boundaries. That's just so that it's clear where the ends of this medium are. So this wave will travel this way, and it'll reflect off of this wall and travel back the other way, and eventually arrive at point A. And when you calculate a path length, you have to take into consideration the full path that the wave has traveled. This wave has traveled this way first and then back that way. And so the path length, which I'll call R2, would be this 2 meters and this 5 meters, so it would be 7 meters. So we have two path lengths here. I've called them R1 and R2, and one of them is simply this distance here, 3 meters, and the other is this distance, 7 meters. And they're just simply the lengths of the paths that the wave had to travel to get from the source to this point that, for whatever reason, we're interested in. Now, the thing that's actually useful here is not so much the path lengths themselves, it's what we call the path length difference. And the path length difference is exactly what it says it is. It is the difference between two path lengths. So in our example here, we had this path length, the direct path length from the source to this point that we're interested in, which was 3 meters. And we had this indirect, reflected path, which had a length of 7 meters. And so the path length difference is just the difference between those. We'll call it delta r. So it's r2 minus r1. So in this case, it would be 4 meters. And I'll just note I chose to make it r2 minus r1 so that it came out positive. There's nothing fundamentally right or wrong about it being positive or negative. For our purposes, we aren't generally going to be concerned about the sign of it. So I'm always going to tend to choose to calculate it so that it comes out positive. Now, let's suppose that we have a source sending out sinusoidal waves, and our system here, I'm going to say, goes from 0 to 8 and has free ends. So waves arriving at 0 or 8 will reflect without flipping. If I'd made them fixed ends so they flip, there's an extra complication, and so we won't think about that. Now, what we want to know is whether this point that I've indicated here as A is a node or an antinode. So first, look at this. We have a direct path length, so waves leaving the source directly get to A with a path length of 4 meters. Waves that leave and reflect off this far end here travel 8 meters. Okay, so that's one of the path lengths is lambda, and the other path length is 2 lambda. And so our path length difference is just 2 lambda minus lambda. It's lambda. Well, so what? Well, that means that waves that leave the source and get here directly will have been traveling for one period, right? A wave travels a distance equal to lambda in a time equal to the period. But they're going to arrive there at the same time as waves that left and came in 2 periods. So direct crests arrive at the same time as reflected crests from exactly 1 cycle earlier. And that means crests are always going to arrive at the same time as crests. Direct crests arrive at the same time as reflected crests, and we could make the same argument for troughs. So that's constructive interference and tells us that this is an antinode. So now let's look at a different point on the same system. Now our direct path is 3 meters, which happens to be 3 lambda over 4, 3/4 of the wavelength. The reflected path is now 9 meters, which is 9 lambda over 4, 9/4 lambda. And so our path length difference is 9/4 minus 3/4, that is 6/4 or 1.5, 3/2 lambda. Well, now that means that crests that get there directly are arriving at the same time as things that left here 1.5 cycles earlier. And 1.5 cycles earlier, what would have been leaving would have been troughs. So crests are arriving at the same time as troughs. And so we'll have destructive interference, and this is a node. Now we know that A is an antinode and B is a node, and so the standing wave pattern would have to look like this. We've just seen a very important general principle. Whenever waves have 2 ways of getting to a point, so that we have a path length difference, if the path length difference is an integer multiple of lambda, so m lambda, where m is any integer, then we will get constructive interference. And if the path length difference is a half integer, so if m is an integer, m plus a half is a half integer, so if the path length difference is a half integer multiple of lambda, then we will see destructive interference.